Today we are going to look at the CYK parsing algorithm for context-free grammars. The nice thing about this algorithm is that it works for every context-free language. And it parses the input word in cubic time with respect to the length of the input. The CYK parsing algorithm is a bottom-up parsing technique. That means it starts from the input word and it works backwards. It tries to reconstruct the starting variable from the input word. The CYK parsing algorithm works with grammars in Chomsky normal form. So if you have given an arbitrary grammar for a context-free language, you first transform it into Chomsky normal form, and then you can apply the parsing algorithm. So how does the algorithm work? We start with a grammar G in Chomsky normal form. If your grammar is not yet in Chomsky normal form, then first transform it into Chomsky normal form. And we want to determine whether a word W is in the language generated by the grammar G. The idea is that we compute sets of variables VU. The U here is a subword of our input W. And the set of variables VU consists of all those variables A from which the word U can be derived. So intuitively it's quite easy to understand what the set of variables VU is, but we want to now compute this set inductively by induction on the length of the word U. So we start with words U that have length 1. If the word U has length 1, it's a single terminal letter. And then the set VU consists of all variables A for which there exists a production rule A rewrites to U. So we look at all production rules that have as right-hand side the single letter U, and we collect all the left-hand sides. And this gives us the set VU. If U is a word that consists of 2 or more letters, then the set VU consists of all variables A for which we have the following, namely, first of all, we can split the word U into 2 parts, U1 and U2. These parts should be non-empty and their concatenation is U. And there should exist a production rule A rewrites to BC such that B is in the set VU1. So in the set corresponding to the prefix of the split of the word U, and C is in the set VU2, so that's the set corresponding to the suffix of our split of U into U1 and U2. And if we have found such a production rule, and B is in VU1, C is in VU2, then A is in the set VU. Now once we have computed all these sets VU for U, a subword of W, then we can check whether the word W is generated by the language, namely this holds, if and only if the starting variable is in the set VW. So W here is the input word that we are given. The worst case time complexity of this algorithm is cubic with respect to the length of the input word. Why is that? Because we have quadratically many different sets of variables, because there's quadratically many subwords U of our input word W, and each of these sets VU can be computed in linear time. Let's have a look at an example. We're going to use the CYK parsing algorithm to check whether the word ABBB is generated by this grammar. And this grammar is already in Chomsky normal form. The left-hand sides are single variables, and the right-hand sides are either 2 variables or single terminal letters. Now we are going to compute these sets of variables VA, VB, and so on, where the subscript here is a subword of our input word ABBB. So A is a subword, B is a subword, AB, BB, ABB, BBB, and the entire word ABBB is also a subword of our input word. We start with the shortest subwords, so with the single letters VA, VB. VA consists of all the variables that have a production rule with the terminal letter A in the right hand side. There's only one such production rule, and the variable on the left is A. VB consists of all the variables that have a production rule with terminal B in the right hand side. Again, there's only one such production rule, and the left hand side is the variable B. The set VAB is computed by looking at all the possible ways to split AB into two non-empty words. There's only one way to split, namely we split into A and B. So what is this set VAVB? VA is just A, VB is just B. So VAB is the set containing just AB. So this means we are looking for all those variables that have a production rule with AB in the right hand side. There's two such production rules. That's S rewrites to AB and B rewrites to AB. So VAB consists of the variables S and B. For VBB, we have to consider all the possible ways to split BB. Again, that's just one possibility. We split into B and B. VB is just B, so VB just consists of BB. We are now looking at for all variables X, such that we have a production rule, X can rewrite to BB. There's only one such production rule with BB in the right hand side, and the left hand side is the variable A. Now it gets more interesting because there is two possible ways to split ABB. Now we have to split into ABB, and we also have to consider the split into ABB. VA is just A, VBB is also A, so this set just consists of AA. VAB is S and B, VB is B, so we get SB and BB, SB and BB. So we look for all the production rules that have either AA, SB or BB in the right hand side. There is no AA, we don't have SB, but we have one rule that has BB in the right hand side. So this set again consists only of the variable A. For VBBB, we have to consider all the possibilities to split BBB. Again, there's two possibilities to split this into two non-empty words. We can either split into B and BB or BB and B. VB consists of B, VBB consists of A, so we get BA, and the other way around, we get AB. So we get BA or AB. We are now looking for production rules that have BA or B in the right hand side. BA never appears, AB appears twice. We have S and we have B. So this set consists of S and B. Now finally we get to VABBB, that's our input word, and there is three possible ways to split this. Either into ABBB, into ABBB, or ABBB. What do we get? From VA, which is A, and VBBB is SB, we get AS or AB. This is AS or AB. VAB is SB. VBB is A, so we get SA and BA. And VABB is A, VB is B, so we get AB, but we already have AB. Okay, so we are looking for all those production rules that have one of these in the right hand side. We never have AS. We have AB, namely for this rule and for this rule. So definitely we have S and B in this set. So we get S and B in this set. SA appears never. BA appears never. So indeed we only have SB in this set. Now we are allowed to conclude that the word ABBB is generated by our grammar because the starting variable is in the set VABBB. Now we know that our word is generated by the grammar, but how can we derive it? So we know that we start with the starting variable S and we want to derive ABBB. So we look at the set VABBB and we look how did we get the variable S here. We got this variable S because we have a rule S goes to AB and we have AB in the set here. And this AB comes from this set here, VAVBBB. So what can we derive from that? We know that we have to rewrite S to AB using this rule. And we know that A now has to generate A and B now has to generate BBB. That's what I'm indicating here, that we have now a variable A that will generate the terminal letter A and B will generate BBB. So from the variable A to the terminal A, it's obvious what rule we are going to use. So let's have a look at how we get from B to BBB. In order to figure this out, we look at the set VBBB. How did we end up with B in this set? We ended up with B in this set because we have a rule B goes to AB and we have AB here. And this AB comes from this set, VBBVB. So what do we know now? We know now that we have to rewrite B to AB. We have to rewrite B to AB. And our A has to generate BB. And this B here has to generate the terminal letter B. So again, we have a variable A that has to generate BB. And B has to generate the terminal letter B. Now let's have a look at this A. We want to generate BB, so we look at the set VBB and we look why did A end up in a set. It ends up in a set because it can be rewritten to BB. And this BB comes from this set, VBVB. So we see here that A has to be rewritten to BB. And each of the B's has to generate a single terminal letter, B. So we basically get this, and now we just have to rewrite each of these variables to a single terminal letter. We do this in 4 steps at once, so we get a BBB.